Well, today is going to be kind of once over lightly of work that's been done by this whole group in this area in the past, I think at least 25 years, maybe more like 27, because my son is 25 and I wasn't even pregnant yet in this next picture. You know, I have to give credit for all the people that were involved in this, including the people on this slide. Certainly Steve Sutton and Matt Newville and Tony Lanzarotti and my current collaborator Molly McCanta, Cody Stephen, who's the current postdoc working on this, and then the person in this picture, second from the end, Jeremy Delaney, who has since retired, but really is the one that dragged me kicking and screaming into trying to understand this problem. So the goals of this talk, oops, go over here, and there we go, are to sort of give you the big picture about why we care about this, and then give you some history and then bring you up to date on what we're doing now. So, you know, the goal of this talk is to really discuss the methods for interpreting XAS spectra to extract information about the solar system. So for those of you who are physicists, this is a slightly different perspective, right? So the first thing I'm going to talk about is why geologists care about this. And I'm going to provide a brief history of the fumbling around we've done to try to use XAS spectra to extract iron valence states. And then talk in more detail about the effects of polarization on these data before I then segue into the insights that machine learning has given us into understanding this problem. So that's where I'm going. So let's start off with the really big picture, planets and asteroids. Why do we care about valence states and why do we use synchrotrons to help inform this problem? And the answer has to do with the fact that in the evolving solar system, oxygen was moving around, and the amount of oxygen that's present when a body forms has a very big effect on what happens, what kind of rocks come out of it, and all of the chemical reactions that happen between the minerals that result. So inside to outside, when you develop a planet or even an asteroid, you need to know how much oxygen was present. Now, it turns out that in this day and age, oxygen remains one of the most stubborn things to be able to measure analytically, and to great frustration of geologists. And so the community pretty much depends on looking at valence state measurements to understand the distribution of oxygen in the early and current solar system. So that's the big picture on why we're interested in this. And of course, if you're looking at oxygen or you're interested in oxygen, then it makes sense that you don't only have to focus on iron valence state, although iron, of course, is the most abundant multivalent element in our solar system. So we're interested in this group and looking at all these different multivalent elements. And to give you a sense, if you're not used to thinking in geologic terms, the x-axis here is the log of oxygen fugacity. So oxygen fugacity is a variable that geologists use that gives you an estimate of indirectly the partial pressure of oxygen that was present in the system. And it's often quoted in different terms. And in this diagram, I have oxygen FO2 relative to iron wustite. So in other words, the amount of oxygen that's present when iron and wustite are both stable. So, our group and many others, of course, are interested in looking at all of these different elements and trying to figure out whether or not we can actually derive oxygen fugacity from measurements of multivalent elements. So there are, of course, lots of other reasons to want to do these measurements. As a mineralogist, I'm interested in the fact that different valence states of different transition metals are different sizes and obviously different charges, and therefore contribute to the crystal chemistry of minerals in different ways. So that's a whole other sideline, and some people are interested in that, or they're interested in the behavior of how these different valence states of multivariate elements, multivalent elements distribute between melts and minerals, or between one mineral and another mineral. But I would say really the holy grail of why we do this is really mostly related to trying to understand the distribution of oxygen throughout the solar system. So that's why you want to do this. And of course, we often have to do this in less than ideal circumstances. So 3 of these pictures, the ones on the right here, are the images from the Hayabusa mission. So Hayabusa sampled an asteroid and brought samples back, but unfortunately it crash landed in Australia. So here are the Japanese scientists looking sad, and here's the crash site. And they were able, because although the canister cracked open, they were able to resurrect a few very, very small particles. And similarly, the Stardust mission that returned a sample from a comet, from the tail of a comet, brought back some dust particles in an aerogel. So, you know, the traditional methods, I've also been working in the field of Mossbauer spectroscopy for a long time, more than 40 years. And Mossbauer is a bulk method for doing valence state determinations. But when you're studying the solar system and you're looking at tiny particles like this, you need small methods. And so we've all been knocking ourselves out to try to develop synchrotron methods to do this. So just to give you a sense of how complicated this is the sort of rogues gallery of the multivalent elements that we're interested in: iron, manganese, chrome, vanadium, europium, and titanium. And this gives you a sense of, for each different element, the fact that the valence state changes result in lots of different changes to the XAS spectra. And it will quickly become apparent that, at least in the geology world, people focus their attention on iron, but it turns out that these other elements in some ways are even more useful for determining valence state. The problem is that they're, of course, not very abundant. And one of the things that Matt and Steve and Tony are working on right now is developing increased sensitivity for analyzing europium valence state, because europium is going to be, I think, incredibly useful given how different the signatures are. So, you know, this is the motivation for all of this. How can we use these multivalent spectra to figure out what the valence state was, so we can figure out how much oxygen was there, so we can understand the geological processes that form this. All right, so let's begin kind of at the beginning. When I started this is now the year before my son was born. A really great paper came out from Sasha Bott, Steve, and Jerry Delaney on using XAS, and in particular using XANES to predict iron valence state. And this is on the right, a picture of the figure from that paper. So this is a magnetite spectrum, which will look familiar to many people on this call. And at the resolution that we had in those days, this is what the magnetite peak looked like. It was this nice, broad, but perfectly symmetrical peak. And it was very easy to remove the spline fit here and then fit the centroid to this. And Sasha and Steve and Jerry figured out that if you plot the centroid of magnetite, which falls here, and hematite and phaolite on a plot, that you got pretty much a straight line. And in case you're not up on your mineralogy, hematite is the end member of oxidized iron, magnetite is 67% oxidized iron, and phaolite is 0 oxidized iron. So, you know, they got this great correlation curve. And just to give you some perspective, up here, this is the detector they were using, or the crystal they were using. And you can see this is what, I think this is a, I don't think that's a magnetite peak. Maybe that's a hematite peak. You know, and then subsequently, of course, we've gone to better crystals. So this paper was great. It gave people a lot of confidence. I'm sorry, this is supposed to be 1994, that maybe there was potential in this. And so that sort of set up a feeding frenzy of people working on the methodology for this, including us. So at X26A, which is where this was all going on at the NSLS, we, you know, developed the software to take a spectrum and, you know, fit the background, and then considerable effort was made to start fitting the pre-edges and try to understand the multiplex structure in these. And, you know, this is where this got really complicated and really frustrating really fast, because it was quickly realized that it wasn't going to be as simple as what Sasha was hoping it would be. And in fact, all these pre-edges, when you looked at them in high resolution, were composed of a bunch of other peaks. And I would say to this day, in mineralogy, we still don't really have an understanding of what these individual peaks correspond to, although with the work that we're doing, which I'll get onto in a few minutes, we're beginning to at least get the data we need to begin to understand how to assign these peaks in the pre-edges. Let's see. So despite that, the community pressed on and decided that they would basically use the centroid of pre-edge peaks to predict valence states. And this has been done in literally hundreds of papers in the last couple decades. And the typical methodology is just what I'm showing. You fit the peaks, and then you take the areas of the peaks, and you basically make a area normalized Preedge centroid, and you plot that area normalized centroid against the percent ferric that's been independently determined by Mossbauer, and you can get a calibration line. So you can already see here that what Sasha originally conceived of, it's just not so pretty in real life, as is almost, nothing is ever as simple as it is when you only have 4 data points. But so we very quickly figured out, and this is a figure that I've had for 20 years, that the calibration lines look different for different mineral groups, and they were a lot different. So that begins to give you a hint of the fact that the Preedge characteristics are way more complicated than the initial work suggested, which is not surprising, and that there's something about the crystal structures themselves that's causing these to be different. Other people tried to study glasses, and some early attempts at making calibration lines with the area normalized Preedge centroid got some nice lines under very controlled conditions. It was never clear how extrapolatable these results were or what the actual error analysis was. So that's sort of those are some of the early work. But I don't think anybody that did any of these studies early on, no one was denying the fact that minerals and glasses have widely variable structures, and so therefore it wasn't surprising when people started trying to do fits to spectra and found out that they all were different. So again, the early instinct was to try to say, oh, well, maybe all of these peaks always line up for the same kind of iron in the same kinds of minerals. But this just turned out to be a very frustrating endeavor. There were a couple of years in there when I had students in my lab that were just doing nothing but fitting peaks to Preedge spectra. And I did all these experiments to see if you set 3 different undergrads down with the same set of spectra, and you say fit Preedges and tell me what the component peaks are, and see if you can get any consensus, and they never could. So that's where that went. Another group, and this method turned out to be incredibly well cited, was an approach taken by Wilkie and that group, which was quite clever. So what they said was, okay, maybe the Preedge peaks actually do sort of kind of represent different coordination environments. So, on the right I have minerals can be 8-fold, iron can be 8 coordinated or 4 coordinated or 6 coordinated. And so they plotted the peak area normalized centroid energy against the centroid area, and they were able to make some plots that look like this. And so, as I said, 400 different papers used a plot like this to try to determine what the redox ratios were in their materials. And it was tremendously non-quantitative, let's just put it that way. Very clever idea, but not quantitative. And as we're about to show in the rest of this talk, pretty much ill-informed because of the orientation effects. And we started looking into this ourselves. This is a study of garnets that we did about a decade ago. So the numbers on these spectra are the redox ratios, and these are all a group called garnet, which is an isometric mineral group. And what you can see is that if you study this long enough, the Preedges, even if you do extract them, there's no linear relationship with the amount of oxidation state of the iron. And then you also quickly see that although, Wilkie and all those 400 papers focused a lot on the Preedge area, that in fact, a lot of the action that's going on in these spectra is really happening at the main edge and out here in the XAS region. And so I think even 20 years ago, we were all starting to think, well, we would have these great arguments at the Beamline about whether we should only collect data on the Preedge or whether we should go further. And the compromise was always, well, take some really high resolution data here at the Preedge and then just do some low resolution data out here. And how wrong we were. So this has been recognized, more recently. There's a really interesting paper by Barry in 2010, which tried to get creative. And, he looked at the data and said, oh, well, maybe if I plot the energy at which the intensity gets to be 0.9, maybe I can come up with a line. and it kind of sort of worked, but the error bars were still pretty bad. This is his method, but some data that came from our group. Another really creative thing he did was he looked at the X-axis region. So this is a blow up of the X-axis region of the spectra, and he said, oh, well, there seems to be kind of an inflection point here, one at 7138 and one at 7.7168 roughly. And so maybe if I ratio those, you know, the great, when in doubt, ratio things together. If I ratio those together, maybe I'll get a straight line. And he did kind of get a straight line. So it was another really creative idea, but not, you know, completely empirical and not grounded in theory. Let's put it that way. Let's see. And then finally, some data that have been collected as part of a project that I'm doing with Molly McCanta. These are class spectra. And so this is, we have way more than this, but at the time this figure was made, 429 different silicate classes. And they're color coded here by the percent of ferric iron, so how oxidized they are. And here you can see kind of nicely, yeah, there's a lot, you know, yeah, the Preedge region shows a lot of potential for predicting ferric iron, maybe, although these peaks all seem to be in pretty much the same place. And again, there's a lot of information out here in the main edge and the XAS region that we could pay attention to. So to bring this little part of this talk together, the early work, in fact, the last 25 years, really convinced us that it really is too simplistic to just use the Preedge. And I don't know how my community got down that path of ignoring everything else, but you know, they took the ball and ran with it, and it did give some useful results, I think, for understanding things in a qualitative way. But the lack of quantitative estimates of errors and the lack of understanding about the crystal structure and particularly anisotropy sort of confounded those methods. So as I'm about to show in the next section of this talk, polarization dependence also turns out to be the reason why this doesn't work. So at that, I will pause for questions.
Thank you. That's really terrific background. There was a question that you're showing us a lot of K-edge data, yep. But is the L-edge any more informative or differently informative?
You know, we haven't taken on the L-edge. Yes, I'm sure that there is information in the L-edge, and yes, I'm sure that the techniques that we're applying to study the K-edge will also work for the L-edge, but we haven't gone there. I guess we could go there, but we haven't gone there yet. I know, Matt, you're also welcome to chime in on any of these questions. You have a comment about L-edges?
So L-edges would be interesting, but they're low enough energy that it's challenging to get a microbeam and do these analysis. And you also want sort of bulk, not just the surface.
Yeah, true enough.
Okay. Another question. You're focusing on the XANES. What about the X-ray emission spectroscopy, especially for the non-iron elements? Has there been much work using that to try to get oxidation state?
Not that I'm aware of. Again, I'm going to defer to Matt on that. This is great. Thanks for dialing in, Matt.
So also, not much work because these are because it's microbeam and the XANES is much easier to measure at quality data than the detailed emission detector.
Yeah, I mean that could change with all of the high brilliance synchrotrons being built. I mean, there's a lot more flux on small spots, which will make it more amenable to XES. But
I completely agree. And doing Herfke and Ricks on these samples is in the foreseeable future and a plan. But the data for the last 20 years, that's not been happening.
Yeah. Okay. All right.
You know, the L-edges have been done in Styxum, for instance, and eels. But again, you have the problem that you have to have a thin sample.
Yep.
So a TEM type thin. And
yeah.
Fluorescence doesn't work very well because the fluorescence yield is low.
Right. And you got to remember that I guess I didn't say this at the beginning, but the actual holy grail for the geological community is to be able to do this on a thin section. So, you know, geologists cut rocks into thin slabs that you can pass light through, and we would really like to be able to just find some crystal in there and, you know, focus on it and figure out how much iron is there.
Right. For those not familiar, when a geologist says a thin section, they mean 30 microns.
Right. The devil's in the details. Okay.
All right. Very, very good. Thank you. You should continue.
All right. So let's talk about pleochroism for a minute. So again, geologists are used to studying minerals using the polarization properties of light. So, you know, the tool that we teach people to use in mineralogy is something called a polarizing light microscope, which allows you to polarize light in an east-west direction and a north-south direction, and then to cross the polars and see what the refraction of light is doing. So again, when we started this, I don't think even I appreciated the fact that although I was teaching students in mineralogy all the time about pleochroism of visible light, that in fact synchrotrons are horizontally polarized. And I think Matt just told me last week that these things are almost, at least at APS now, it's almost completely horizontally polarized. So I think the geologists didn't appreciate this fact when they were doing the historical development of this technique, and yet they should have, because, you know, figures like this, it's well known that visible light travels at different velocities depending on the orientation of the crystal, just like visible light does. And of course, this phenomenon happens because the density of atoms in different orientations is different. So you can't just expect to be able to put your sample in front of a polarized synchrotron beam and not expect that interactions will happen that are going to affect what your spectra look like. And again, this is about 20 years ago, we had this sort of horrifying realization, and Nikki Gunter and I wrote a series of papers which developed the techniques for doing these kinds of measurements and showing just how important this effect was. So this just to give you some pictures of what these look like. So these are pairs of the same crystal mounted on the end of a glass fiber with nail polish at different directions. And even in these images, you can see they're different colors in different directions. And of course, that also means that the synchrotron images of these things are going to be different. These ones on the bottom here are from a paper that we did on asbestos amphiboles, which was kind of neat. And at the time, we developed a geometry for the beamline that looks something like this. So it's not your usual beamline geometry. Basically, we mount that little crystal that you saw is right here in the middle, and then to the left there is the goniometer head with the spindle stage on it, basically. And then you'll notice that we have the rotating stages down here, and the beam is looking directly down on the sample. So we don't come at a 45-degree angle. We actually come directly down here in order to make the math work. And to explain this a little better, here's actually a drawing. So here's how we did these measurements. So on the left is a little illustration of a polarizing light microscope. We take that single crystal, we mount on a glass fiber, as I said, and then we use this polarizing light microscope to orient the crystal. And you can see here's the little goniometer head mounted on the microscope stage. And by using the characteristics of polarized light, you can figure out which setting on your goniometer head corresponds to the important optical directions in your crystal, which I'm going to call X, Y, and Z for the purposes of this talk. So the way we're doing this to this day is we use a polarizing light microscope, we orient the crystals, and then we have a gajillion of these goniometer heads. So we mount the crystals, orient them, record the optical orientations, the settings on the goniometer head that correspond to the optical orientations. And then we pack these things up and ship them to wherever we're doing the measurements. And then we put them on the beamline, and here's another photo of the geometry to give you a better sense of this. So here's the stage, here's the goniometer head now mounted there, there's our little crystal, and you can see that the photons are coming perpendicular to the axis of the goniometer head, if you will. And then here's a little close-up of what this looks like up close. So we have to use a special beamline geometry, which makes us really popular with Matt and the other guys there. And when we do this, again, these are old measurements, but it's such a nice set. So these are, in each case, it's the same sample, and these are just pre-edges, the same sample, and you can see at different orientations, the pre-edge magnitude varies dramatically with orientation, which is exactly what you'd expect. It's exactly the way optical spectroscopy behaves too. And one of the things that we're doing now with with our postdoc Cody is trying to understand how the orientation dependence of optical spectra, which are pretty well understood, relates to the orientation dependence of the component peaks in the XAS spectra. So I think that's going to be a pretty exciting direction to go. These are some more recent spectra. We're working on a mineral group called Pyroxene, which turns out to be pretty ubiquitous in the solar system. And these are just two different samples, and now you see the whole spectral range, and you can really get a sense of the orientation dependence of these phases. So this is here we were calling them A, B, O, B, and O, N, but they're actually X, Y, and Z. And you can see that at least in this mineral group, the Preedge doesn't change a lot with orientation. It does change somewhat, but there's a huge amount of change up here on the main edge and then out into the XAS region. We used to call these Pyroxene spectra bunny ear spectra, and sometimes the bunny had both ears up, and sometimes the bunny only had one ear up. So we knew that there were some weird things going on with orientation in the old days, but we didn't have the data to prove it. Now we have we have the ability and the technique down to orient these spectra, and we can see that these differences are huge. And because of that, it kind of puts a nail in the coffin for using the Preedge approach, because as we said back in 2002, we actually calculated the errors that you get depending on which orientation you're at, and we found out that you get absolute errors of 10 to 15% on determining ferric iron if you don't pay attention to orientation. So that set off a whole other decade of inquiry to answer this next question, which is how can we overcome orientation effects to develop better, more universal prediction methods. So with that, I'll stop again for questions. I'm leaving you hanging.
That was really, that's really interesting. Could you go back to that figure, the slide that has the 8 different materials on it, perhaps? Each with 3 different orientations. Yeah. What are some of these minerals? It's all acronym. Which,
oh, sorry. Yeah. So these are micas. That's biotite, muscovite, biotite, muscovite. And let's see, these are pyroxenes and amphiboles. So these are kind of important rock-forming mineral groups.
Okay. Okay. There's a question, how was your work on orientation effects greeted by the community?
Not well. People were in denial. And I don't have a slide in this talk about this, but there were a lot of people who said, well, okay, to get around this, I'm going to put my crystal and rotate the stage. And by then I'll get a bunch of different orientation effects. But of course, those people aren't thinking about the fact that in a usual geometry on a beamline, your beam is coming in at a 45-degree angle. And so if you rotate rotate your sample on a stage and your beam is coming in at 45-degree angle, you're not getting what you think you're getting. So yeah, this was not received well, but grudgingly.
Okay, very good. Then I'll ask you to continue with the next part of your talk.
All right. Okay, so what's the answer? The answer, the punchline is that we spectroscopists, full tilt, anybody that does any kind of spectroscopy, are facing a paradigm shift in our field, I think. And I've been going around actually to institutions and giving another talk that's called The Future of Spectroscopy, in which I say that any field that's dependent on looking at little blips in spectra at any wavelength is due for a massive shift. The way I had my eyes open to this was actually pretty funny. One summer I had a bunch of undergraduates working in my lab, and 3 of them were doing what I was talking about earlier, which is they were fitting peaks to pre-edges ad nauseum, because we had hundreds of spectra that they needed to fit. And it just so happened that that summer I also had another undergrad in the lab who was working on web development for another NSF project. And the students were talking one day. I was in the lab, and one of the pre-edge fitters was explaining what she was doing to this kid, and there was sort of a long pause, and Marco said in a very loud voice, "Well, that's really stupid." And Erica said, "What do you mean? That's what Darby told us to do." And he said, "You could do that with multivariate analysis, and it would be a lot easier and a lot more quantitative." And so I went up and said, "Okay, wise guy, prove it." And an hour later he did. I kid you not, an hour later. So, you know, we had been struggling with these garnet spectra to get consistent peak fits and to do the peak area average centroids. And, you know, our correlation coefficients were like, yeah, you know, 0.85, 0.89. And, you know, an hour later, Marco showed me a plot and the correlation coefficient was 0.995. I was like, no, this can't be right. And anyway, to make a long story short, darn it, he was right. And that led me to seek out some colleagues at UMass who kind of educated me in learning how to do some of these machine learning techniques. And that's what the rest of this talk is about. So back to this plot here. So as I said, this is a collaboration with Molly McCanta where we synthesized a bunch of silicate glasses at different oxygen facacities and measured the redox ratios with Mossbauer. And so, you know, you look at this peak, you look at a group of spectra like this, and you try to think about the way I was taught 40 years ago, which is how do you parameterize this kind of data, these kind of data. And, you know, in those days, yes, I would have said, okay, I'm going to try to plot the intensity here against the intensity here, or, you know, I would do some creative thing. But machine learning, it has huge advantages over this because it doesn't prioritize. It takes a very unbiased view at all wavelengths. And of course, it doesn't have the bias that we have, which is we're trying to understand, you know, we have preconceived notions about where these peaks should be and what should be causing them. And machine learning is completely agnostic in that way, which is both bad and good, but sometimes it's good. So let's talk a little bit about some of the methods that we can use. So really one of the first machine learning methods to do this kind of regression analysis was developed in the 1960s, and it's called partial least squares analysis. You can find subroutines that do PLS in every analytical library. And basically, the problem in spectroscopy that we have is that most of the channels that we have are collinear. And so because they're collinear, you really are not supposed to use multiple regression kinds of methods because of that collinearity. So PLS is just a mathematical way of projecting the data into another space. And when you do that, you remove the collinearity because the new directions in your new space are orthonormal. So that takes away that problem from ordinary least squares regression. And it just creates two different matrices. And it can actually do fits in that orthonormal space that produce coefficients for each channel and create coefficients. So it's actually quite elegant and simple mathematically. I won't go into it, but essentially every spectral channel gets treated as an independent variable. The thing you want to predict, which in this case, of course, is oxidation state or maybe oxygen fugacity, becomes a dependent variable. And then you have some kind of matrix that ends up looking something like this. So does it work and what are the advantages? Well, the short answer is yes, it does work. I'm going to convince you of that in a minute. But it has some other byproducts that are also really advantageous. One of them is that when you do PLS analysis, it tells you, as I said, it outputs the coefficients, which are plotted on the right-hand side of this figure and also as dots here. And of course, as with any kind of coefficient, the further it is from zero, the more weight that particular channel has on the regression. So not only does PLS give you a regression expression, but it also tells you where in your data set the most important channels are. So this happens to be, these are vanadium K-edge spectra, and this is from a paper by Tony Lanzarotti that I should have put Tony's reference on. But what you see quite quickly is that there are, you know, it's not kind of what you thought. Yeah, the important channels are, some of them are here in the Preedge, certainly, but there's a lot of really important information, you know, that's not right on the Preedge, and in fact, it's not on the main edge either. Some of it's on this sort of, I don't know, there's some interesting channels out here in the XAS region, but many of them are kind of shy of the, or just over the top of the main edge. So, you know, understanding what these PLS coefficients are telling us is a whole area that, you know, we don't have a methodology for yet, but I think it's got great potential. So yes, that's one advantage of multivariate analysis. Back to this thing. Okay, so for the glasses, that was the first, really the first material that we tackled because the glasses are anisotropic by definition, so we didn't have to deal with the orientation effect. So when we first did a calibration for the glasses, we actually ran samples both at NSLS and at APS, because at that point we were kind of transitioning over to APS, and you know, happily the calibrations are perfectly collinear. We've played around a lot with whether we should correct for absorption. It doesn't seem to be absolutely necessary. You know, another way in which these machine learning methods kind of what's the word? They go against your spectroscopic biases, is that some of the things that we thought we always had to do, the machine learning methods are able to kind of see through. And of course, our goal now is to actually be able to make these calibrations available as part of the Beamline software, so that people anywhere can use these, as long as they normalize their data in the same way we do, and as long as they offset to the same standard which we use for iron metal. They can use our algorithms and get really nice, accurate measurements. So they can predict ferrous ratios in glasses from a wide range of compositions with really high accuracy now. So that's pretty exciting, and we're working with Matt to get this into sort of an institutionalized software. Another kind of machine learning method, and of course there are many of them, and these are, we've only scratched the surface of this. These are just the pretty early on developed ones that are kind of generalizable. Is something called lasso regression. So lasso regression is kind of it's a takeoff of multiple regression, your old friend y equals mx plus b, et cetera, et cetera. Only basically what it does is it's shrinking that regression expression to reduce the number of terms. And the reason this is important is because we would like someday to be able to acquire XAS spectra fast. And in particular, I'm going to show you, we want to be able to do mapping. And of course, we can't do mapping when it takes 10 minutes to do 1 pixel. So lasso is useful to us as a multivariate technique because it allows us to figure out what are the most important channels. And so you can adjust there's an adjustable parameter in lasso called alpha. And so, for example, you can adjust alpha in such a way that you only have 4, it tells you which 4 channels are important. And you can dial that number to be anything you want. But in this particular case with the glasses, we dialed it to be a small number so that we could actually make maps. And so we played around with that. We got some really interesting results. So here's an example of, again, these are some of those glass spectra. And with 4 channels, if you do a predicted versus known plot, you get something that's not bad. And even 2 channels gives you something that's not bad. I mean, R squared is still 0.91, but still it's 0.91. So why do we care? Well, we did, and again, Molly's on the line, I think also, we did a really neat experiment where we were looking at glass beads that came from volcanoes on the moon. And, to go back to what I started this talk was, one of the things that we're really interested in understanding is what is the oxygen content on the interior of the moon. And so by looking at volcanic glasses that were erupted really fast, we can actually get a sense of whether the interior of the moon is inherently reducing or inherently oxidizing. And so we made maps. You can see these are all the pixels, and we just used those 4 channels, or in some cases we just ratioed 2 channels together, and we were able to get some beautiful maps of lunar glass beads. And we can contrast these then with maps of other elements in these things to try to understand more about whether the oxidation front is moving out or moving in. And so Molly and I wrote a paper about this, which talks about the reduction that can happen as the gas cloud expands, or the fact that you can also get redox zoning. So the zoning, it turns out, can either go in or out. And in one handful of glass beads, well, not even a handful, a tiny aliquot of glass beads, we could see both kinds of behaviors in the lunar samples, which is really neat. And the reason this is interesting to a geologist is that looking at maps are the way geologists make sense of spatial things in rocks. And so the fact that you could only do point analyses by XAS was frustrating to us. And so being able to push this technology so we can map is huge for us. Here's another cool example of some crystals. These are glass beads that actually have crystals growing in them. And the crystals are olivine in this case, and olivine does not like ferric iron. So there's no ferric iron in the olivine at all. So what you have is this beautiful image of the olivine crystals with no ferric, and then the background glass has lots of ferrous. So, or not lots, but has a different content. Just to sort of show you how well this works. So garnet, the mineral that's isometric that I showed you lots of pictures of earlier, we can get almost a perfect prediction of ferric iron and garnet now by using the lasso. Amphibole we're still working on because amphibole is profoundly anisotropic. So I will return for a few slides then to the topic of anisotropy and these things. So an important thing about, to generalize this talk even further, is just to say that the methods that I'm talking about work, you know, obviously for XAS spectra of all types, but they're also going to work for everything else. They're going to work for L spectra. They're going to work for any other kind of spectra that you care to work with, from spectra of galaxies that are acquired, you know, by a telescope, down to other kinds of things that are done at microscales. Let's see. They, these are pictures of, this is the same mineral, this is the same group of minerals actually, and these are spectra of 4 different multivalent elements that we're interested in. And they're all fascinating and interesting in their own ways. And when you look at these, you can you can see, once you start to come away to this way of thinking, it's hard to imagine that the community spent 20 years just being focused on pre-edges, because clearly there's so many more rich features in these things to look at. Finally, we had another realization, which is an outgrowth of our work with machine learning, that basically said, well, wait a minute, you know, the machine learning methods are dumb in the sense that they don't know what you're predicting. So in our case, you know, we have theory to suggest that, you know, these features are going to vary with the valence state of iron, or with whatever multivalent element you're interested in. But then it occurred to us, well, wait a minute, what about the oxygen partial pressure? What if there's something about the XAS spectra that's going to tell us something about the partial pressure of oxygen? So we tried actually just predicting FO2 directly from the XAS data. And again, this is, oh good, I did put the reference here. This is from Tony's paper. And yes, you can predict oxygen fugacity beautifully with this method. So you don't need to determine the valence state and then from the valence state infer oxidation state. You can, I mean, you can infer oxygen fugacity. You can just predict oxygen fugacity directly. So, you know, machine learning for me has been kind of a continuum of starting out with things that I knew, you know, like I know that valence state should be affected, that should affect XAS spectra, to saying, okay, well, let's see what else we can predict with these data. And so it's an incredibly enlivening possibility. And we now have a tool. I don't need the grad students anymore. We have an online tool that the undergrads can use, where you can just upload a data set and say, predict this variable and see how well it does. And it's you know, as I said, this kind of exploration is going to change spectroscopy forever. But to get back to Zanes for a second, or for XAS, we've learned a bunch of lessons in the last 25 years. The first one is that you have to account for X-ray pleochroism, and I'm going to let Cody's talking, and we'll get him signed up to talk about what we're doing with this now. But the key to understanding the diversity that we see in XAS spectra is that if the material is anisotropic, you have to acquire reference spectra of the principal orientation directions. And then once you have the spectra of the 3 end member orientations, then all other spectra are some vector combination of those three end member vectors. So the trick to this is that you have to account for the pleochroism, and unfortunately the only way you can do that is to actually acquire spectra at those orientations. And as you saw, that's incredibly difficult. Right now, there's only a couple people in the world, I would say, that really know how to orient the spectra correctly. So we're hustling to try to get as many calibrations done as we can. And of course, the more, you know, the Achilles heel of everything that's multivariate analysis or any kind of machine learning is you have to have lots of training data. And so that's, you know, costly and difficult, but we've been very fortunate that both NASA and NSF have supported this work, and that we've been able to get beam time on the synchrotrons to do it. I mean, the part of our problem now, I think, is that we're still developing the calibrations, and the community is rushing to use it. So we can't do the calibration fast enough to keep people from actually using our premature data, which is driving us kind of crazy. But Anyway, yeah, my vision for the future is that we will eventually have pre-existing calibrations for different minerals and, of course, for other different materials. And, you know, I have to say, though, that as empowering as I think machine learning is, I like to think of it as a tool that will help us understand the fundamentals of spectroscopy. So I think it can go the other way. And the example I always give with this is that I also do something called laser-induced breakdown spectroscopy. And in that technique, we're doing something, you know, very similar to this, also using PLS. But an outcome of a recent study was that we were able to find some new emission lines for trace elements. So, and it was because the machine learning line said, look, this channel, you know, we looked at those regression coefficients and we saw channels that were highly correlated with cobalt. And turned out they were cobalt emission lines that nobody had ever reported. So, you know, machine learning isn't just one way. It isn't just take data and get conclusions. You can actually sometimes take your conclusions and work backwards and understand something that's fundamental. And as a trained spectroscopist, I love that. So I think that's my last slide. I'll stop. Well, I'll leave the sharing on in case anybody wants to look back at one of these slides. Thank you so much.
Thank you. There's a bunch of questions. That was fascinating. Samantha, would you like to start?
Hi, yes, thank you for your talk. I had a question about your predicted versus truth plots for your lasso channels. It seemed that the data was clumped into two different clusters. I was wondering why.
It just has to do with this. Well, maybe this is it just has to do with where we had standards. So, for example, in this group, yeah, it would be really nice if Mother Nature made standards that went all along this line, but they don't. You know, for various reasons that have to do with crystal chemistry, you can't necessarily find samples that occur along the continuum. So this has been part of the problem, is that we have to when making these calibrations, we have to find standards that actually, you know, represent a range of, in this case, oxidation state. And sometimes that's just not possible because nature doesn't make them that way. So yeah, there's nothing significant about that. It's just that was the standards that we happen to have available to us. Good question.
All right, John, you had a question?
Yeah, John must be muted.
That's okay, I got it. He's curious if your methods are robust against errors in energy calibration.
So we've played around with that a little bit. I mean, it is certainly true that you have to be very careful how you pre-process the data. And we have a very careful routine that talks about, you know, how to do the edge step normalization, how to calibrate against iron so that, you know, everything is exactly in the right energy range. So yes, if it's not calibrated correctly, then the algorithms don't work. So everything has to be, that is, I guess, a weakness. Everything has to be processed exactly the same. But that's not going to be a problem because most of us on synchrotrons, we all use the same routines anyway. So once we kind of build these routines into the Beamline software, then everybody by definition will do it the same.
Okay. Matthew Marcus, you had a question?
Yeah, I was wondering about the prospects for analyzing samples in which there are 3 or more valence states coexisting, such as, for instance, the manganese in enviro systems often comes in 2, 3, and 4 together.
Yep. Yes, I mean, you know, this is a regression technique, so you don't only have to predict one variable. So, I mean, there are different flavors of these, right? There's PLS1, which predicts one variable at a time, but there's also something called PLS2, which can do predict multiple variables at the same time. So yes, we haven't gone there, although I think we will, because especially with vanadium and manganese, also we're going to end up with kind of more complicated problems. But yeah, there's no reason why you can't just predict all of them at once.
Yeah, and it may be more robust to just try for the average valence state.
Yes, you could also do that, right?
If I can interject, actually the Lanzarote paper was looking at vanadium, which it does have multiple valence states. So. Part
of the problem, though, of course, is that we don't have independent ways of knowing what the valence state is. Well, that's not true. We do. If you can do it with optical spectroscopy, but you know, in a lot of the materials that people study, you are making an assumption about what you think the valence state is in your standard. So you know, that's another big bugaboo with this, is that with the iron, it just so happened that I had Mossbauer data on all these minerals, which is why we were able to do these calibrations pretty handily. But we don't have huge databases sitting around where the valence state of sulfur, I haven't talked about sulfur, but sulfur is another application of this, or any of these other minerals are actually known, especially the ones that are mixtures. So yeah, that remains to be seen, whether you can take only N members and then use machine learning to figure out what the intermediates should look like. But you know, we'll get there eventually.
Okay. Wanli, you had a question?
Hi, thanks. I was just wondering, have you ever seen any sign of iron 4+ in oxide? This is not directly related with this talk, but I noticed you listed iron 4+.
Yep, and and the reason it's on there is because, you know, as I said, I do Mossbauer spectroscopy, and there is iron 4+ in some combustion products of coal, for example. So the higher oxidation states of iron are known in some organic materials, and I do have Mossbauer data of them, but I've never actually looked for it, and I've never done it with Zanes. That's a really good point. I mean, I have those materials. I probably ought to just put them in and see what they look like.
Yeah. So the Mossbauer data is conclusive on the
yes.
Okay. Thanks.
If you want to see those references, just email me and I can send you some papers on Mossbauer of the higher valence states of iron.
Okay. Thank you. Very interesting.
All right, Tim, you have a question?
Hi, very nice talk, thank you.
Thank you.
My question is this sort of multivariate analysis or machine learning? Well, I assume what you're doing here is what we call standard resolution Zanes, meaning that if you're using high resolution Zanes, it's essentially not necessary for these studies by using those mathematical models, or would actually, if you were doing this on high resolution Zanes, or your 439 spectra, for example, you could actually get even better improvements in your correlations and answers.
Well, it turns out that that's not necessarily a given. And I know this because, again, we've used these techniques in LIBS, which is atomic emission spectra, so not the same phenomenon, but related. And so with LIBS, we've experimented a lot with how the resolution affects the measurements. And of course, you know, we all know that if you have a normal distribution, as long as you have a very minimum number of points to define it, you can define it pretty well. And this is a case where the machine learning methods kind of help us a lot, because I think that the higher resolution is not necessarily going to give us, at least this has been our experience with LIBS, the higher resolution doesn't necessarily give us more accuracy, which is nice. For once, something is easier than you expect it to be. But I really haven't much played around with this. I mean, to give you an idea, these, you could probably tell from some of these plots, those our typical setup for the minerals is now about, I think it's about 400 channels across. So it's not a huge amount of data, mostly because of time restrictions. But it seems to be sufficient. I don't know. I mean, Matt, do you have a sense of whether higher resolution would help us? I mean, we're going to need it for europium. Sorry.
So I would say that it's a maybe, and we're going to try,
Yeah.
but it may not be dramatic. But it might. But like you say, for other elements, titanium, vanadium, europium, it might be better.
Yeah, it kind of depends on what the structure of the spectra is.
And as you hinted at, it might also be useful for picking out an additional variable, like you hinted at, LASSO and PLS can do, not simply valence state, but some other variable for these minerals.
Absolutely. I mean, any
give some information on coordination that's perhaps not always available in the Zanes.
Yep.
Right, or yeah, magnetic, yeah, right, something. Yeah.
Yeah,
all right.
any parameter that is, I mean, any number that you can parameterize like that can be predicted. As I said, just as we were predicting the FO2, there's, you know, if there's other information, that's an interesting point. I haven't tried to predict coordination number, but it could probably be done. I'd have to think about having the right standards to do that, but that's an interesting idea.
Last question, Matthew Marcus.
Yeah, I was wondering about some of these. There are oxides like FeO and sulfide FeS2, where the edge looks almost like a metallic Fe, even though it's nominally 2+. And I was wondering if your methods even come close to getting the right answer.
You know, again, that's something that we could look at, and we haven't yet. And I have the right samples to do that, to answer that question. But I will say,
calibrate on it, then of course you're going to get the right answer.
Yeah, well, that's true. I mean, that's the problem. You have to have enough samples that you could calibrate on it, and have enough things that were unknowns that you could still try to predict it and get a sense of your accuracy. But my overall sense of the machine learning methods from all the different kinds of spectroscopy I do is that anything where you look at the spectrum and you sort of say, gosh, those are different in some subtle way that I can't put my finger on, that when you throw machine learning at it, machine learning will figure it out. So that's why I in fact, I think that's where machine learning excels. Like, for example, in atomic emission, machine learning excels at actually finding the trace elements there. And they are very subtle inflections in the spectra, and yet the machine learning can pick them out. So any kind of problem like this, where the differences are pretty subtle, if you can get if you have enough standards, you can our community is going to be surprised. 20 years from now, our community is going to be looking at these data in a very different way than we look at them now.